So one class of groups that is often used in cryptography are based on elliptic curves. An elliptic curve is a third-degree equation between x and y. So the equation reads y squared equal x cubed plus ax plus b. A and b are the constants that define the curve, and the x and y are solutions to this equation. And it is possible to define the addition of 2 points on the curve to obtain the third point. This is depicted in this diagram. What we see here, 2 points P and Q. And if we draw a line between these 2 points, we will always find the third point. This can be proven. This is a characteristic of elliptic curves. And we define the addition as the point which is reflected with respect to the x-axis. So this is a way, an intuitive way, to define addition over points on an elliptic curve. Now, what we see here is that the underlying field, so the x and the y, they are chosen from the field of real numbers. But in cryptography, actually what we do, we use the underlying field as a finite field. You can think of it simply as arithmetic modulo some large prime number. In this example, the prime isn't large, it's small, just to make it visible. The prime is 97. And as you can see, we get all these pairs of points between 0 and 97 scattered over the two-dimensional grid. So this is how an elliptic curve looks. So it doesn't look like a curve. The fact that we are using a finite field means that all the geometric intuition goes away. We can't see it there. So to recap some things, the geometric interpretation only makes sense over the real numbers, but algebraically you can change the underlying field to any finite field modulo p. So here we see, I invented this notation. So the curve with parameters a and b over the finite field f of p are the pairs x and y that satisfy the equation. And by the way, that equation is a particular equation known as the Weierstrass form. But these are details about elliptic curves that we're going to skip. It is obvious that this set, the set of points is finite. It is a subset of Fp times Fp, the Cartesian product, and we are sort of have to believe this. We have to accept that the set of point is closed under addition, making it a group. And so this is what we see here. We are not going into the details of how this addition is implemented. This is a separate area, and we can spend days discussing elliptic curves. But you can think of it as sort of as a black box. It's a group operation, and it works. So one thing you really must take care of is that we are talking about addition, whereas when we are doing the multiplicative group modulo a prime, we are doing multiplication. So sometimes this leads to confusion in the notation. To get a cyclic group, what we do is we choose a base point B, so we choose a point on the curve, and we consider the group which is generated by this point B. And in additive notation, that means that we are going to consider B, 2B, 3B, XB, up till MB, supposing that M is the order of the group, of the base point. If you would write the same thing multiplicatively, then you would do something like that. I changed the B for the G to be consistent with the earlier notation we used. But it's the same thing. It's the same math, but the notation is different. So this is something that you have to be careful about. Despite the additive notation for elliptic curves, we still speak about the discrete log problem on elliptic curves. So the discrete log problem here, we have g to the power x, whereas in the additive notation it's x times b. So it would not be a discrete log problem, but so kind of a multiplicative problem or division problem. Anyway, this is not what people say. There are even people that will even continue to use the multiplicative notation when talking about elliptic curves. I am one of them because I worked so many years with multiplicative group that for me it's hard to go back to the additive notation. Now, what do we know about the size of this group? Now, that is not an easy question. There are some heavy theorems underlying this. But what happens essentially is that the size of this group can be, with right choices of parameters, it can be the size of the prime number, more or less. When I say more or less, I mean this in the size of the number of bits. So the size of the number of bits of the group is about the size of the prime number. And so this we can choose parameters, the prime number, the constants a and b, and the base point, such that we can find a group whose order is 2 to the 256 or 2 to the power 384, and this corresponds roughly to a security level of half the number of bits. This is an important thing you should be aware about, and I will discuss why this is so in the next few minutes. Note that there are also curves that allow pairings, and this will be discussed later on when we will talk about the KGG bit commitment scheme, about polynomial commitment scheme, sorry.